Welcome back to the Deep Dive. As always, we're diving deep into the world of math.
And today,
We're going even deeper
send it to me.
into a specific sequence from the OEIS A000169 to be exact.
Well, right.
So this sequence accounts the number of labeled rooted trees with n nodes. And the formula for this sequence is surprisingly simple. It's an equals n to the power of n minus 1.
So nice, clean formula there.
Yeah, exactly. But turns out this simple formula, it actually shows up in a bunch of different areas of math.
It does.
So today we're really going to try and understand why this formula is so important, and we're going to explore some of these connections that it has.
I think that's a great goal.
Yeah, so I guess maybe just to start things off, can you maybe give us like a super clear definition of a labeled rooted tree, just so we're all on the same page?
A labeled rooted tree on n nodes, it's basically a tree, which means it's a connected graph with no cycles. But the key here is that each of the n nodes, it has a unique label, so you could label them from 1 to n, for example.
Okay, so like the nodes are distinguishable?
Yeah, exactly. They're not all the same.
Gotcha.
And one specific node is chosen as the root of the tree.
Okay, so there's like a special node.
There is a special node.
Gotcha. That makes sense. And so let's look at like the first few terms of the sequence just to get a feel for it.
Okay.
So for n equals 1, we just have a single node.
Right.
And that's also the root.
Yes.
And that's just one possibility.
One possibility.
And if we plug that into the formula, 1 to the power of 1 minus 1, that's 1 to the power of 0, which is just 1.
Yeah.
So it matches.
That's the formula.
Exactly.
Right.
Now what about for n equals 2? What do these trees look like?
For n equals 2, we've got 2 labeled nodes.
Okay, let's just call them
We can call them 1 and 2.
1 and 2. All right.
So we can have 1 as the root with 2 as its child.
Okay.
Or we can have 2 as the root and 1 as its child.
Gotcha. And those are different.
They are different because the root is different.
Okay.
And also because the labels are different.
Okay, so that gives us 2 labeled rooted trees.
Exactly.
Yeah.
2 possibilities.
Okay, and 2 to the power of 2 minus 1
Is 2 to the power 1.
Yeah, which is 2.
Which is 2. So again, it matches the sequence.
That matches. Okay,
Correct.
cool. So now for n equals 3, things get a little bit more complicated.
They do get a bit more complicated, yeah.
But the sequence tells us there should be 9 of these trees.
That's right, 3 squared.
Yeah, 3 to the power of 2, which is 9. But it's a little bit hard to visualize all of those different
It's
trees.
a little harder to just draw them all out.
Yeah. So can you maybe talk about like what kind of structures we would be seeing there?
Yeah, so let's think about it. We've got our 3 nodes,
Okay. Labeled 1, 2, and 3.
1, 2, and 3. And one thing we could do is we could have one node be the root.
Okay, and then the other 2.
And then the other 2 would be its children hanging off of it.
Gotcha. And because the children are labeled?
And there are actually 3 choices for which one is the root.
Okay. Because we could pick any of the 3 to be the root.
Exactly. And then once we've chosen the root, there's only one way to arrange the 2 children.
Okay. Because they're
labeled.
They're labeled. So that gives us 3 trees right there.
Okay. 3 trees where the root has 2 children.
Right. But there's another way we could do it.
Okay.
We could have the root.
We could have a root.
Well,
with one child.
Okay. And then that child has another child?
And then that child has the 3rd node as its child.
Okay. So it's like a chain.
It's like a little chain, yeah.
Gotcha. So in this case, again, we have 3 choices for the root.
3 choices for the root, because it could be any of the 3 nodes.
Okay. And then once we've chosen the root, there are 2 choices for like the middle node.
2 choices for who gets to be the root's child.
Yeah.
It's exactly.
The last node is just the grandchild.
Okay. So that gives us 3 times 2.
3 times 2, which is 6 trees.
Okay, so 6 trees that look like that.
Right. And if we add those 2 cases together, 3 plus 6.
Yeah. That gives us our 9.
We get our 9 labeled rooted trees.
Okay. For n equals 3?
For n equals 3. So we've got our 9 trees.
Okay, that's really cool. So it's interesting that, like, the labels are really important here. Yeah. They really make a difference.
Because we didn't have the labels.
If we didn't care about the labels, some of those structures would actually be the same.
Yeah, okay. That makes sense. So I guess like the main point here is that this formula, n to the n minus 1, it really does count. These labeled rooted trees.
It does. That's its main job.
Yeah. But it turns out that's not all it does.
That's just the tip of the iceberg.
Yeah, like you were saying before, this sequence shows up in a lot of surprising places.
It really does. It's a bit of a celebrity in the math world.
So what are some of these other places where it shows up?
Well, one example is these things called connected transitive subtree acyclic digraphs.
Wow, that's a mouthful.
It is a bit of a mouthful, but
Yeah.
it's a really cool concept.
Okay, so what exactly is a digraph?
A digraph is like a regular graph, but
Okay.
the edges have a direction,
Okay, so they're like arrows
like arrows.
instead of just lines.
Exactly. And acyclic means that there are no directed cycles.
Okay, so you
You can't follow the arrows around in a loop.
Gotcha. Okay.
And transitive means that if there's an arrow from A to B
Okay, and an arrow from B to C.
and another one from B to C, then there must also be an arrow from A to C.
Okay, so it's like,
It's like a shortcut. Yeah.
gotcha. So this whole thing connected transitive subtree acyclic digraphs.
Right. It sounds very different.
It sounds very different from counting labeled trees.
It does sound different on the surface.
Yeah. So how are they related?
Well, it turns out that there's a way to match them up.
Okay, like a one-to-one correspondence.
Exactly. It's called a bijection.
Okay. And I don't think we need to go into like all the details of the bijection.
No, I don't think we need to get into the nitty-gritty.
Yeah. But the fact that it exists.
The fact that it exists is really important.
Okay. Because it means that.
It tells us that these two seemingly different things, they actually have the same underlying structure.
Okay. They're just encoded in different ways. So it's like two different ways.
Two different ways of representing the same
Yeah.
information.
Oh, okay. That's really cool.
And they both happen to be counted by this n to the n-1 formula.
Gotcha. So it's like they both have this.
They both have this same essence.
Yeah, this same like mathematical essence.
Yeah, exactly.
Okay. That's really fascinating. So the OEIS also mentions that, this n to the n-1. It also counts the number of functions from the set 1, 2, up to n.
Right. To itself.
Yeah. Such that the sum of the function values is congruent to k modulo n for any given integer k.
For any k that you choose.
Okay. So how do functions even fit into this picture?
This one is really cool because it brings in some algebra.
Okay. Along with our combinatorics.
So imagine we've got our n elements.
Okay. And we think of them as nodes in a graph.
Okay.
So
For each I, from 1 to n, our function f, it takes I, and it maps it to f of I.
okay. So we can think of that as.
And we can visualize that as an arrow
Okay.
in our graph.
In a graph going from I to f of f.
Gotcha. So we've got all these arrows.
We've got all these arrows
Yeah.
representing our function.
Okay. And it turns out that if you look at the big picture, this collection of arrows, it breaks down into a bunch of connected components.
Okay. And each component.
And each of these components, it's basically a cycle.
Okay. With some trees attached to it. Yeah.
So imagine like a loop and then some trees kind of hanging off of the loop.
Okay. Pointing towards the loop. Gotcha. And the condition.
And the cool thing is the condition about the sum of the function values, modulo n.
Yeah.
It actually tells us something about the properties of these cycles and trees.
Okay. So it's
It's like a hidden connection between modular arithmetic and the structure of these graphs.
Okay. That's really cool.
Yeah. And if you count carefully, the number of functions that satisfy this condition, you get n to the n-1.
Wow. So yeah, we see this formula popping up.
It pops up again in a totally different context.
Yeah. So amazing how it connects like trees to mappings and then to modular arithmetic.
Yeah, it's like for you.
It's like a bridge.
Yeah. Connecting all these different areas.
It's connecting all these different parts of math. Okay. So I guess moving on. There's also this really simple observation that the nth term of a geometric progression with the first term 1 and a common ratio n is n to the n-1.
Yeah, that one is super simple.
Yeah. But is there like
Yeah.
more to it?
Sometimes the simplest things are the deepest.
Okay. You never know.
You never know. It could just be a numerical coincidence.
Okay.
But it could also be that there's some deeper connection, some hidden structure that we haven't uncovered yet.
Okay. So it's worth paying attention to. Gotcha.
Even the simple things.
Okay. So then there's also this connection to rational solutions
Yeah.
of x to the y equals y to the x,
Ah, yes. That one's a classic.
where x is less than y.
Where x is less than y. So
Yeah.
it turns out that these solutions, they involve ratios
Okay. Of terms.
from our sequence and another sequence.
So it's like a combination.
So it's team effort.
Yeah. Okay. And that's a pretty unexpected link.
It is a bit
Say
unexpected.
the algebra problem.
Yeah, it's like algebra, combinatorics, joining forces.
Yeah. To solve this equation. Okay.
Yeah.
So can you maybe explain a little bit more about how that connection works?
Sure. So the rational solutions to this equation, they look like this. X equals 1 plus 1 over n.
Okay. To the power of n
Okay.
and y equals.
And y equals 1 plus 1 over n to the power of n plus 1.
Okay. And this is for some positive integer n.
So if you try to write these solutions in terms of integers, you'll find that they involve powers of n plus 1 and powers of n.
Okay, and that's where?
And that's where the connection to our sequence comes in.
Okay.
Because our sequence is all about powers of n
Okay.
and n minus 1.
Gotcha. So it's like...
So it's like this problem in continuous math, solving this equation, it actually has this discrete combinatorial connection.
Okay, that's really neat.
It is pretty neat.
All right, so moving on, the OEIS also says that a of n plus 1 is the number of partial functions on n-labeled objects.
Partial functions?
Yes, those are interesting. So
Can you explain what a partial function is? So a partial function, it's like a regular function.
yeah.
It doesn't have to be defined. For every element in the domain,
Okay, so some elements.
the elements might not get mapped to anything.
Gotcha. Okay.
Let's say we have n labeled objects.
Okay. And we want to map them
Yeah,
to n plus 1 objects. Okay,
Yeah.
so for each of the n objects in the domain.
right. We have n plus 2 choices.
Okay, we could map it to any of the n plus 1 objects in the codomain.
Exactly. Or we could just leave it undefined.
Okay, so that's n plus 2 choices.
Right, for each of the n
Each,
objects.
everybody.
But the connection to our sequence.
A of n, it actually comes in when we're talking about partial functions.
Yeah.
From n objects.
Yeah.
To themselves. Okay, so
The domain and the codomain
the domain and the codomain
Okay.
are the same.
are the same. Okay.
So
Girl.
in that case, for each of the n objects, we have n plus 1 choices.
Okay. Because we can map it to any of the n objects.
Exactly. Or we can leave it undefined.
Okay. So that's n plus 1 choices.
Right. For each of the n objects.
Yeah. And so the total number of partial functions is n plus 1 to the power of n.
Okay, which is exactly a of n plus 1.
Okay.
So it's
So it's like
four.
adding that extra choice of being undefined, that bumps us up to the next term in the sequence.
Okay, that makes sense. So it's all about that extra option. Okay, cool. So the OEIS also gives us another perspective in terms of binary relations.
Binary relations.
So
Yeah.
it says that a of n is the number of binary relations on a set of size n minus 1 that are also functions.
Right. So this one is a bit subtle.
Okay, so let's break it down.
Let's break it down.
Okay, so first of all,
What's a binary relation?
yeah, what is it?
A binary relation, it's basically a way of connecting elements from two sets.
Okay,
So let's say we have a set A
okay,
with n minus 1 elements.
right. A binary relation
Mhm.
from A to A. It's just a bunch of pairs.
Yeah.
Where each pair...
Where the first element
Yeah.
is from A, and the second element is also from A.
Okay. So it's like...
So we are connecting
Oh.
elements within the same set
Gotcha.
and a function
Okay.
is a special kind of binary relation. Okay, where each element in the domain.
Where each element in the first set is related to exactly one element in the second set.
So in this case, the
Okay.
OEIS is saying that the number of binary relations on a set of size n minus 1 that are also functions
Mhm.
is A of n.
Mhm.
Okay, but there's a subtle difference here.
There is a subtle difference, yeah.
Okay, what is it?
The OEIS is actually talking about binary relations that are functions from a subset of the set.
Okay, to the original set.
Okay.
So it's not necessarily a function on the whole set.
Not necessarily in the whole set, just on a subset.
Gotcha.
So
okay.
let's say the subset has k elements
Okay. Where k could be anything.
from 0 to n minus 1.
Okay. So
There are n minus 1 choose k ways.
to choose the subset
Because we're choosing k elements.
out of n minus 1.
Gotcha.
And for each element in the subset, there are n minus 1 choices for its image.
Okay. Because we can map it to any of the n minus 1 elements in the original set.
Okay.
So the total number of binary relations that are functions from a subset of size k is n minus 1 choose k times n minus 1 to the power of k.
Okay. And then X per speaker.